Hello everyone, this is Dr. Zach. So today we're going to understand the differences between continuity and differentiability. Today we're going to take a look at the lesson preview. There's some really important information. Depending on your last name, you either found the derivative of the sine or the derivative of the cosine, but both are going to provide excellent ideas to think about. So using the definition of your derivative, you found through substitution that you had the limit as your delta x goes to 0, sine of x plus delta x minus sine of x. And there you got stuck unless you remembered your trig identity dealing with the sine of a plus b. So this is one of those trig identities that belongs in your list of identities if you didn't already place it in there. So once you have used your trig identity, the next thing you should do is look at the sine of x as compared to the function sine x cosine delta x. Gather those together and factor out your sine of x. What conveniently happens is you will notice that the cosine of x minus 1 over delta x is in the problem, and it goes to 0 as you apply delta x going to 0. Also, you have the sine of delta x over delta x, which goes to 1 as your delta x goes to 0, which leaves us with f prime of x, or the derivative of x, f prime of x, is equal to the cosine of x. The derivative of the sine is equal to the cosine. This is the second takeaway for question A. Question B was very similar in many aspects, except you were looking for the derivative of your cosine in this problem. So as you did your substitution, similar things happened. We needed to expand the cosine of x plus delta x using the trig identity. So write that trig identity in the list of things you know. Afterwards, we regrouped the cosine of x with the other term with cosine x. Very conveniently, the cosine delta x minus 1 over delta x goes to 0, and the limit as delta x goes to 0 for sine of delta x over delta x goes to 1. There we have it. What we now know is that the derivative of the cosine is equal to the negative sine of x. Your fourth takeaway from this very important lesson preview. Make certain you have both of these ideas written down, or all these ideas written down, so that you can use them later. All right, let's jump right into this. We're looking for the differences between continuity and differentiability today. So let's talk about differentiability. A derivative is actually a limit. The derivative is used to describe the slope at a point. So for the slope at a point to exist, there are a couple conditions that must occur. The point must exist. The limit of the slope must exist. Now you've got to come from both sides for that. But not only that, the limit of the slope has to equal the derivative or the slope at that point. So this follows from the definition of continuity. So for a derivative to exist at a point, several things must occur. Your function must be continuous. So you're going to have to know that the limit as x approaches a from the left side of the function is equal to the limit as x approaches a from the right side of your function, but that must also be equal to the function evaluated at a. This guarantees that you have continuity. Now, talking about the left slope equals the right slope, we're going to use a similar notation. The limit as x approaches a from the left of f prime of x has to be equal to the limit as x approaches a from the right of f prime of x, but that also has to be equal to f prime at a. So all of these conditions must occur for our derivative to exist at a point. Now, let's look at our 4 examples I have here. We're going to talk about where it's continuous and where the derivative does not exist. Or does exist. Take a close look. For example 1, you should see a vertical asymptote at -2 and the function's undefined at 2. So we know that our function is continuous everywhere except for 2 places. We're continuous from -∞ to -2, We're going to skip the -2 and head on over to 2, skipping 2, and then we go to positive infinity. So that's where we're continuous. But if we are not continuous at -2 and 2, then we certainly are not differentiable there. We're going to look at all these slopes. Now, as you think about where this function is increasing and decreasing, all of these are nice smooth curves. This function is actually differentiable everywhere except for the same places. So we're going to be differentiable, and we're going to make the same list for differentiability for this first example. Now let's look at example 2. So as we explore example 2, thinking about function f of x equals the absolute value of x minus 2. As you can see, this function is continuous over the entire interval. There is nothing bothersome about this function. So we're going to be continuous from -infinity to infinity. However, let's talk about differentiability. Can you see that the slope is heading downward to the left of 2? And then it's heading upward on the right of 2? We have a problem at x equals 2. So it's continuous everywhere, but the limit as x approaches 2 from the left of f prime of x is not equal to the limit as x approaches 2 from the right of f prime of x. And because of that, this function is not differentiable at x equals 2. So if asked where the derivative exists, it exists everywhere except -2. Matter of fact, f prime at 2 does not exist. I think I was saying -2, but it's at 2. If you are asked where is the function differentiable, it's going to be differentiable from -infinity to 2, union 2 to positive infinity. As we look at example 3, do you notice we have a step function? So the step function makes it kind of obvious. The derivative, it's not continuous at x equals -1, 0, 1, 2, etc. So it's not continuous at those points. But it's also not differentiable at these values either. So not differentiable at x equals -1, 0, 1, and 2. So we have the jumps, which makes the function not differentiable. As we saw in example 1, it's the same in example 3. So where is this differentiable? You would write differentiable ... establish a pattern from -2 to -1, union, -1 to 1, union, 1 to 0, and then throw in some more dots. All right, let's look at example 4. This one is a very interesting example. Now, what I'm hoping is that you do see that the function is continuous along -infinity to infinity. But something very interesting is happening as we approach 0. If we look at the derivative as we approach 0, let's see here. What is the limit as x approaches 0 for f prime of x from the left side? Now, from the left side, do you see that that derivative seems to be going upward to be vertical? And it's heading towards positive infinity. But if you take the limit as x approaches from the right side of 0 for f prime of x, it's also, well, let's see here, heading towards, oh no, it kind of looks like negative infinity as you head downward. It's a vertical tangent line. So when you have a vertical tangent line, that messes everything up. What happens at the vertical tangent line is the derivative does not exist. So f prime at 0 does not exist because you are going to either infinity, negative infinity, and that is not okay. So we have a vertical tangent line, which means our derivative does not exist. Today's lesson practice involves a bit of exploration. So for about 30 minutes, no more than that, I want you to use Desmos. Desmos is a graphing utility online, so www.desmos.com. If you've used this before, that's great. If not, it's very easy to learn. I want you to use the functions and answer the questions related to each one of these functions. Do your best to answer these questions first, and then you can check your work once you're finished. Make certain that you write most of your answers in interval notation. So turn the video off now, complete the problems, and check your work later. As you look over your answers, keep in mind that the derivative cannot exist where you have vertical tangent lines, and I believe those occurred at both x equals 2 and negative 2. For the sine function, you cannot have horizontal tangent lines at the endpoints that are not in your domain, so keep that in mind. And also take a look at where your function is increasing, decreasing, as where as the derivative exists. Number 5 is definitely a line, and it has a hole in it at x equals 1, negative 1. So your derivative exists everywhere except at negative 1. Now, sketching h prime of x. Since h of x was a line, its slope given is 3. The derivative must be 3, and so the graph is a horizontal line at 3 with a hole at negative 1. So looking at question 6, the slope at 3 is equal to 2 if we estimate using the tangent line that was given. We also want to write the equation of your tangent line, y minus y1 equals m times x minus x1. Now for number 7, determine where the derivative is 0. So those are your horizontal tangent lines, which occur at negative 0.5 and 1. Also, determine where f of x is increasing. So to me, it looks like we're increasing between those two values. When I sketch my graph, I first put the zeros in. Afterwards, I said it's increasing, so it must be positive. Then the rest of the graph is decreasing, which makes f prime of x below the axis on the other sides of negative 0.5 and 1. So we want to know if f of x is differentiable at 6. So first understand that it is continuous. What I did is graph the picture. I can see that it's continuous because it's an absolute value function. Next, let's look at the derivative on the left side of 6. As we approach 6 from the left, the derivative is negative 1. As we approach 6 from the right, the derivative is positive 1. Therefore, the derivative at 6 does not exist. Next, a piecewise function. We want to first show that f of x is continuous. We take the limit as x approaches 2 from the right, and we end up with a 5. The limit as x approaches 2 from the left, we end up with 5, so f of x is continuous. Differentiability. First, let's say that the derivative is going to be 2x for x is less than 2, and 4 for x is greater than 2. We then know that the limit as x approaches 2 of the derivative from the right is equal to 4, and as we approach 2 from the derivative on the left, it is also 4. Therefore, f prime at 2 must equal 4. Now, as you work with the sine function, make certain that you are in radian mode. You are always in radian mode for calculus class, very different than physics class. Once you did all the work, you should have come up with h prime of x is negative 2 over x to the 3 halves. And when you substitute your 3 in, you get some ridiculous looking answer. All right, now it's time to think about trying some homework on page 105. Please don't do 74, 89, and 90. And once again, do not work for more than 60 minutes. So less than 60 minutes and you have a great day.